We are aUToronto from the University of Toronto. In this presentation, we will be addressing the issues of the road salt contaminant in the wintertime for our Mobility Innovation Challenge 1. As you can see, here in Toronto, we get a lot of snow, around 1.3 meters annually. To combat the freezing weather, we deploy lots of road salt after the snowstorm to make driving safe. While road salt melts the snow and lowers the risk of annual accidents caused by snow by 88%, it presents new challenges for autonomous vehicles on the road. The hard-to-remove salt snow slush mixture splashed on the autonomous vehicle's sensors degrades their perception capabilities even though the weather is nice, like right now. Safety is very crucial for autonomous vehicles carrying passengers, and therefore, we seek a solution to guarantee perception capability. Over time, the constant salt splashes also harm the car's chassis integrity as salt is corrosive to metal. Unnoticed rust could create numerous problems, such as hydraulic brake system leaks to subframe damage, all of which could cost fleet owners thousands of dollars for repair and decreases fleet safety. This presents a unique challenge of how we can both increase the maintenance frequency while minimizing the downtime for the vehicles. With these challenges affecting the safe operation of autonomous vehicles and the increased cost of fleet maintenance, we seek a solution to address the unique challenges in the northern regions.
You might wonder, what are the options out there? There are currently multiple technical approaches for enhancing the visibility of perception sensor, such as vibrating sensors, wipers, and electric field repellent solutions. And for fleet maintenance, automated solutions such as car wash tunnels are also very common. The table here is a comparison between our proposed solutions and our evaluations regarding their feasibility and effectiveness. As you can see, there is no single solution that can solve these road salt problems at once. Therefore, we propose an ensemble solution to mitigate this problem and tackle this challenge collectively. Our three-tier approaches start with a preventative measure of adding a chemical coating to the sensor's optical pane to mitigate the problem from the source. In addition, we have an algorithm to detect the perception of sensors and the condition of the sensor, and a mechanical wipers with a fluid jet to remove the residue during the ride. And lastly, in an attempt to service the vehicles frequently, we introduce a target maintenance system with the use of mobile manipulator while the vehicles is charged at a charging station. Our first tier of solution aims to address the problem from the source, utilizing a chemical coating on the sensor optical pane. This chemical mixture, a type of hydrophobic silicon polymer, will effectively reduce the possibility of salt snow mixture from sticking to the optical sensor by increasing the roughness of the surface of the optical pane. After applying the chemical coating on the glass pane, we can see that fluids are being repelled more frequently. Therefore, coating will reduce the likelihood of any salt snow mixture or residue sticking to the optical sensor. This solution can be easily implemented with just an additional manufacturing step when creating the sensor's enclosure. The solution can be applied through a thermal spray process with an estimated manufacturing cost of about $40 per 4 square feet surface area. To implement this solution on aUToronto system, we can use a commercially available kit for car, such as the 3M39901 coating. We believe that this solution is feasible, effective, and widely scalable in an attempt to prevent the problems of road salt from the source. This solution reduces the likelihood of low concentration of salt solution hanging on the optical pane. The higher concentration of salt mixtures will still leave residue on the optical sensor, decreasing its performance to detect the objects.
Our Tier 2 solution utilizes both a mechanical and a software approach to remove road salt slushy contaminate on the sensor's field of view. The mechanical design consists of the LiDAR wiper setup, the camera wiper setup, and a washer fluid sprayer system. The camera wiper design is mounted on the lower side of the sensor suite. A dedicated wiper assembly is used for each camera angle. For our design, we selected a standard automotive wiper motor. It can generate continuous rotational motion with adequate torque output through a worm gear setup. The rotational motion is converted to an oscillating wiping motion through a sliding slot mechanism. Overall, the wiper's motion spans the area in front of the camera, potentially removing all salt contaminant in the camera's point of view. On the other hand, the LiDAR wiper assembly is mounted on the top side of the sensor suite, directly on the structural U channel. The LiDAR wiper solution is the combination of a stepper motor-driven belt and pulley system and a wiper carriage mounted on the ball bearing guide rail. The belt and pulley system converts the rotational input from the servo motor to the linear motion of the wiper carriage. The resulting motions allow the wiper to slide linearly in front of LiDAR, accommodating the special perspective field of view of the sensor. The washer fluid sprayer system sprays water onto the weatherproofing panel to improve the efficiency of the wiper. It allowed the system to more easily remove stronger contaminant adhered to the panel surface.
While wipers provide the physical capability to remove the residual that sticks to the optical pane, we still need to have a method to detect and evaluate the degree of obstruction and decide when to wipe the sensors. To achieve this capability, we utilize the power of machine learning and neural network. We create a machine learning model based on ResNet 18 and train it on the Canadian Adverse Driving Condition dataset, allowing it to detect if obstruction is present on the perception system. To further quantify the level of obstruction and decide when to take action of the mechanical wipers, we utilize a secondary fully convolutional neural network to segment individual patch of obstruction on the view. The mechanical wiper is only activated when the perception is obstructed to a certain extent and affects the safe operation of the autonomous vehicle. To minimize the impact of mechanical wipers obstruction the view, we utilize optical flow and the neural network to remove the wiper in post-processing. To maximize the perception system capability, our wiper system software are designed such that at least one sensor modality is operational for the corresponding perspective field, while the other ones is being cleaned by the wiper. While the wiper solution is helpful to guaranteeing maximum visibility during driving, it does not address the concern of chassis deterioration from the salt snow slushy on the vehicle chassis. To address this concern, we propose a smart maintenance facility system. We envision that modern-day autonomous rideshare vehicle will be electrically powered. Every time when the vehicles are being charged at a charging station, the exterior of the vehicle shall be thoroughly cleaned. While we could add an automated car wash tunnel at each charging station, the infrastructure cost puts a burden on the fleet owner, resulting in a higher operation cost. Instead, we propose a mobile manipulator-based system that cleans the exterior of the vehicle. The mobile manipulator platform will be similar to how airport de-icer vehicles de-ices the plane. Through a perception algorithm similar to our Tier 2 solution, the camera on the manipulator detects exterior contamination on the vehicle chassis and washes it down utilizing high-pressure water. We believe this method minimizes the infrastructure cost for autonomous vehicle fleet and allowing the mass deployment of cleaning capability to each charging station. Additionally, targeted washing also minimizes the water usage for each vehicle, reducing it from 120 gallons to 15 gallons, saving the amount of water waste and reduces the environmental impact. The manipulator-based approach also allows controlled pressure minimizing impact on the vehicle's perception sensors.
When it comes to the feasibility and economic harms associated with winter driving, our solution can help expand autonomous vehicle fleet implementation in colder climate areas and impact society by providing a safe and satisfactory experience. With autonomous vehicle ride-sharing becoming commercialized, we believe our solution can enhance developers' confidence and minimize the hazard of having a poorly maintained vehicle. In addition, the hardware we propose to use is effective while being cost-efficient. Total cost per vehicle is marginal compared to the cost of a total vehicle sensor system, and the additional infrastructure costs associated with the mobile manipulator inspector is well less than having human labor in a large washing establishment. Proper maintenance expands a vehicle's lifetime by several years and saves an amortized $500 per potential occurrence of rust on chassis. The reduced financial overhead further facilitates fleets to lower the trip cost for end consumers and allows the money to be spent on other service improvements.
Autonomous rideshare vehicles provide the community a transportation system without discrimination to end users, as we have discussed in our past social responsibility reports. Various concerns on autonomous vehicle safety hinder this new transportation method in being implemented in colder weather regions. We are hopeful that our tiered solution can address the concerns related to winter road salt contamination and reduce technical barriers to bring this new modality of transportation to colder weather regions around the world. You can find more detailed technical information in our technical report. Thank you for watching our presentation.